So hello everyone, welcome to the channel. So in this video we're going to talk about image registration using control points. So let's get started. So in this video we will demonstrate the application of the procedure just developed by registering one image to another. The same procedure is used for registering an image to a map to remove the geometric distortions by using an image to image example through. It is easy to highlight some pitfall that must be avoided. The example we have chosen involves a portion of two Landsat multispectral. The scanner images of a region in the northern suburbs of the city of Sydney, Australia. So one was acquired in 1979, another image was acquired in 1980s. We have only shown one of the near infrared bands here. Once those bands have been registered, all the bands can be registered using the same control points and the mapping polynomials to generate a registered color product. So clearly there is a major brightness difference between the two images, that is 1979 and 1980s. Since they have been recorded in a near infrared, both healthy green vegetation and the urban regions show as a bright, water shows as a black. So you can able to see from this image here, the water bodies being indicated in dark color, so in both the images, and similarly the urban areas being indicated in the bright color in both the image. And from here the dark gray regions are the burned vegetation areas resulting from forest fire. In the 1979 image, so there is a major forest fire in the image that is indicated in both the plus mark here, which indicates the forest fire. Comparatively, in 1980s image, the most of the forest has been revegetated, but new forest fires are evident. So you can able to see from the image here, the plus mark here indicates the forest fire areas, the burned areas, and this is a 1980s image. But comparatively in 1979 image, these are the forest burned areas. You can able to see that this portion entire the dark gray color which represents the forest fire areas. So but comparatively 1980s, most of the forest areas been revegetated, but still it indicates the forest burned areas here in 1980s, which indicated in the plus mark here. So in most of the 1980s has revegetated, but two new, the forest fire are evident here. So the one to the northwest on the boundary of the river, and another in the central southern part of the same area. So you can able to see this. There are geometric differences between the images as well, even through they are less evident. It is by registering the 1979 image. So let me repeat it. It is by registering the 1980s image to the 1979 image that we will remove the geometric differences between them. Had the 1979 image being the map, then that could had the 1979 image been a map, then that could be the map to remove in geometric distortions from the 1980s image. Our first task is to choose a set of ground control points. So on this slide we have shown two different sets of control points. Those on the top tiers of images are well distributed over the scene, whereas those on the bottom images tends to be clumped. You can see the difference here between the top and the bottom images. And with the bottom images, the none of the control points are towards the image edges. Notice that we have chosen the control points on the water and land boundaries. As much as possible, those sorts of control points should be on the headlands and not on the river inlets, so that the tidal variations are minimized. In general, we should choose as a control points features which do not changes in position from an image to image. So the road intersections the good as our corners and our buildings and the fields. So in this example, we're going to use a third order mapping polynomials and cubic convolution resampling. So this slide shows the result of the registering a 1989 image, the slave, to the 1979 image, the master, using the good set of control points. There is a set that was well distributed over an image, covering all the part of the image. In order to demonstrate how well the registration has worked, we have displayed the master image as a red and the slave image as a green. The reason for doing that is that where the images are in alignment geometrically and have an approximately the same brightness, the combination will appear yellow, which is an additive combination of red and green. So here we see that the registration is very good. Apart from the color differences due to the 1979 and 1980s, the forest fire scars, the combination is yellow with no obvious red-green separation. The other red border is just a part of the 1979 scene for which there is no 1980s coverage. The fire scars colors are interesting. The 1979 scar shows as a green because there is very little red signal from the 1979 pixels, whereas the 1980s fire scar shows as red for the same reason. So the 1979 fire scars are shown in the green set of color here, and similarly the 1980s fire scars are shown in the red set of colors, which is indicated here in this image. So there is a very little 1980s signal in those portions of the image. Now this slide shows the result of the registration using poor sets of control points. Where the control points were bunched, the registration is very good, but beyond the distribution of the control points, the registration is very bad. Note especially the red and green offsets around the edges of the water. You can able to see here, and similarly here the green portions. Note in the yellow color we can see that that the 1980s image has been stretched out of shape across the diagonally. We now wish to understand that behavior, so we can get a good idea of well behaved and poorly behaved registration just by looking at the fitting a curve through a set of points as shown in this slide here. So the first image here shows the first order fit. So here the first order equation matches the distribution of the points moderately well and seems to be extrapolated in a well behaved manner beyond a set of control points. There are a set of points. So the second order curve gives a slightly a better match to the points, but seems to diverge unnecessarily beyond the data points. Finally, the third order mapping polynomials can be made to fit the data points more closely than other two mapping orders, but it behaves quite radically beyond the extent of the data. In other words, it does not extrapolate well. The general lesson we learned from this exercise in curve fitting is that the low order polynomial may not fit a set of data points as well as the higher order polynomials, but in general terms they will extrapolate better. In contrast, the higher order polynomial may match the available data better, but will extrapolate poorly. So from this slide, the third order mapping polynomial fits a region of the image in the cluster of the control points very well, but beyond that region it extrapolates poorly. That gives us a particularly an important guide in the choice of the control points. As far as possible, the set of control points should be distributed uniformly across the same and enclose the region of the image for which an accurate registration is important. And if there is any doubt about the distribution of the control points, then a lower order mapping polynomial should be used. So this slide demonstrates the benefits of using a lower order mapping polynomial. When the distribution of the control points is not so good, it uses a poor sets of control points from the previous example. The result of that example is shown on the left side of this slide, the left hand side of this slide. So remember this was generated using a third order mapping polynomial without changing anything else. The image on the right hand side was generated using first order mapping polynomials. As observed, the extrapolation of the Ritz 1980s image ingrained is much better than when the third order mapping polynomial we use. There will be a greater registration error in the vicinity of the control points, but that is not noticeable visually in this simple case. So just by a reminder, every band of an image has to be registered or corrected in this manner, provided the band-to-band registration from an image supplier is good. The same control points in the mapping polynomials can be used. So the key points that is covered in this video is we have seen the importance of selecting a control points that are well distributed over an image to be corrected. The control points should be a feature that are unlikely to change in time between the images if the image to image registration is of interest. The edges of water body can be a problem if you are choosing your control points over the water, and a higher order mapping polynomial gives a low registration errors near the control points but can be poorly behaved away from the control points. If there is a concern about the distribution of the control points, the lower order mapping polynomials should be used. The example here used was a cubic convolution resampling. And remember, every band of an image has to be registered, but the same control points and the image polynomial should be able to be used if the band-to-band registration for an image is from the good supplier is good. So in this video, I have shown you the image registration using control points and an introduction to remote sensing. So thanks for watching, and subscribe to our channel and give us a like, and make sure that you follow us for the upcoming videos. Thanks for watching.